The derivative as a function. So the goals here, understand the concept of a derivative function. We're going to see how that differs from what you've used before. Understand how to find higher derivatives. I want you to understand that sometimes there's a need to go to the second derivative, the third derivative, the fourth derivative, etc. Understand the relationship between f of x, f prime of x, and f double prime of x. And we're going to look at that in more of a graphical sense rather than an algebraic sense. And then be aware of the different notations that are used for derivatives. There's actually quite a few. And even though you will typically just use a couple in practice, I want you to be aware that there are others. So let's go ahead and take a look at the derivative function to start out. And first thing is just recall the definition of a derivative allowed us to find the derivative of a function at x equals a. So our f prime of a was equal to the limit as h goes to 0 of f of a plus h minus f of a all over h. That's what you worked with before, and finding derivatives at a single location is good. There's nothing wrong with that. But having a function, f prime of x, that we can use to find the derivative at any x value is better. If you have some generic f prime of x result, and you can just plug an x in and get the slope of the tangent line at that point, that's better. So all we're going to do is modify the definition to be as follows. And it's a really easy adjustment. You just have f prime of x now equaling the limit as x, or h, goes to 0 of the f of x plus h, then minus f of x all over h. So all you're doing is just leaving it as an x instead of some a. And that's all there is to it. That's the derivative function. If you work out the right side, you will get a representation of your slope of the tangent line, your instantaneous rate of change, with this variable x in there that can be replaced by any old value that works. That's all there is to it. So let's go ahead and move into the higher derivatives. And for higher derivatives, this concept has many real-world applications, the overall derivative concept. And one involves the physical application of motion. If you're looking into the physics world as a path that you're going to go on, you will see motion being part of that in certain places. And in this scenario, you let the f of x represent position at a given time. So basically your x variable will get turned into time. So your x-axis is the time axis, and then all your y values, your f of x's, are going to represent positions. So they usually use units like feet or meters or miles or whatever, and your y value will be so many miles or so many feet, your position at that time. Well, the f prime of x will represent the change in position at a time. And when you're changing position over time, you've got velocity. So, and more importantly here, you've got the instantaneous velocity from your f prime of x in this scenario. But we don't have to stop there. You don't just, in modeling motion in the real world, have position and time and have those go together to become your velocity. When you look at the change in position over time, you can actually have change in velocity over time, or an instantaneous rate of change of velocity being measured by f double prime. So you have the f double prime representing the change in velocity, and that's going to be your acceleration. And in fact, you can go beyond that to get the jerk, as they call it, which is your third derivative, your f triple prime. So based on this idea, it should make sense that sometimes higher derivatives are needed beyond the first derivative. If you're modeling motion, you got to use position, you got velocity, you got acceleration, you got jerk, and from what I understand, there's even one beyond that. So stopping at the first derivative isn't a thing in that scenario. You got to go further. So that's what they mean by higher derivatives. You need second, third, maybe fourth. And in order to get there, we're just going to fall back to the derivative definition for guidance. So if I want to find f double prime of x, I'm going to take the limit as h goes to 0 of f prime of x plus h minus f prime of x all over h. So to get to the second derivative, you basically start at the first and then use it. So let's see how that works in an example. We got the f of x equaling 2x squared minus 3. I want to find f prime of x and f double prime of x, and I'm going to start by finding the first derivative. So f prime of x is going to equal the limit as h goes to 0. I'm going to have the x being replaced by x plus h. So I'll have this 2 times x plus h quantity squared minus 3. And then minus the f of x, which is just the 2x squared minus 3. That will be all over h. And then we can do some algebraic manipulation here to get to our answer. So I got to take that x plus h and square it, which means it's x plus h times x plus h. Got to FOIL that out. So we'll have the 2 there, and then we'll have x squared plus 2xh plus h squared. And then minus 3, and then we'll distribute in, we'll get a minus 2x squared, and then plus 3 all over h. And at this point then, I can cancel some things out. Looking at it, I have a negative 3, I have a positive 3. Those can go away. I will have a 2x squared that's positive when I distribute in up front. That will cancel out with my negative 2x squared. And then I can move to the next step here, and we'll get the limit as h goes to 0. Looks like we'll get a 4xh when I distribute that 2 into the next term there. And then I'll get a plus 2h squared all over h. And looking here, each term, the 4xh, the 2h squared, the h has an h in it. So I'm going to be able to take one h out of everything. And what we end up with then, moving to the next line here, we got a limit as h goes to 0 of 4x plus 2h. We could do a direct substitution to find the limit, and plugging h is equal to 0 in, we just get 4x. So this is our first derivative. The f prime of x is equal to 4x. And kind of reiterating how useful this is compared to just f prime of a, notice I can just plug any x value in and get the slope of the tangent line at that point with this 4x result. So pretty nice. And let's go ahead and move forward then and find our second derivative. So f double prime of x, we're going to use the f prime of x result. So we'll have the limit as h goes to 0, and then we'll have f prime of x plus h. So I'm just going to have 4 times the quantity x plus h minus the f prime of x, which was just 4x, all over h. And again, we have some things that can cancel. Distributing in, we get a 4x. That will cancel with our minus 4x. And then we'll just have the limit as h goes to 0 of 4h over h. The h's cancel and we just get 4. So our second derivative here is just 4, a constant. In a real world application where we're looking at the position, the velocity, the acceleration, f double prime is acceleration. So we'd say here we have a constant acceleration of 4 units per time unit squared. You're usually looking at things like feet per second squared, or sometimes they'll say feet per second for your acceleration. But at any rate, it's constant, and that's how you do it. You essentially use an iterative process, as they call it. To get to your first derivative, use the original function. To get to the second derivative, use your first derivative. To get to the third, you would use your second, and so on. All right, so let's go ahead and take a look at the relationship between f of x, f prime of x, and f double prime of x. So one thing that is important to understand is this relationship between f of x, f prime of x, and f double prime of x, and maybe further, but let's just focus on the first three here, so to speak. Now, conceptually, the relationship is that f prime of x represents the rate of change of f of x. It's an instantaneous rate of change, your slope of the tangent line. And remember that the rate of change can be thought of as that slope. I can't stress this enough. Knowing that f prime gives you slopes of tangent lines is a huge thing to take away from here. So if we look at this graphically, we can build the graph of f prime by just knowing the graph of f of x. So how do we do this? I don't want to run out of time. I know it's early, but I was doing this earlier, to be honest, and I ran out of time. So I'm going to go ahead and pause this video right here, and we will see how this works in part 2.